All right, quick summary from yesterday. What did we do? We said if we have rational functions, right, polynomial divided by polynomial, then we don't even have to really do anything. We can just, by inspecting the polynomial, we know what the limits are going to be at infinity, right, where the horizontal asymptotes are going to be. We know based on just the degrees of the two polynomials, if the top degree is less than the degree of the denominator, then we know that the limit at infinity, plus or minus infinity, they both go to 0. So we get the result is we get a horizontal asymptote at y equals 0, which is just the x-axis. If the degrees of the numerator and denominator, if both polynomials are equal, then we know that we're going to get a horizontal asymptote, and the limit is going to be equal to the ratio of the leading coefficients. And then the third case, if the degree of the numerator is bigger than the degree of the denominator, then we know we don't get horizontal asymptotes. Okay. Remember that rational functions always share a single horizontal asymptote on both sides of the graph. Left and right share the same asymptote. And I think that brings us up to speed. Any questions? Okay. So the next step then is to look at kind of a pseudo-rational function. It's actually not a rational function because the bottom is not a polynomial, right? It's a square root of a polynomial. But our same thinking could still guide us here, okay? Any ideas how we might approach this? And just kind of think back to what our approach was yesterday, what we do with these things. Let that guide you. Any suggestions? Jonathan, idea?
Find the highest degree.
Say it again.
Find the highest degree.
Okay, the degree of the top is 1, the degree of the top polynomial. The degree of the polynomial in the square root is a 2, but I think you're meaning the right thing. Yeah. Want to add to that? Okay, sort of. It's not really a polynomial, but which of the terms, if we're taking limits at infinity, when I say at infinity, I mean plus or minus infinity, right? Which of the terms in each of those polynomials is going to dominate? If x gets huge, which term in a polynomial dominates the behavior of the polynomial? Well, but I mean, take them separately. Like, look at the top polynomial. It's got 2 terms. Which term is going to dominate when x is large? 2x, right? In the bottom polynomial, which term is going to dominate when x is large? X squared, right? The leading term dominates. So let's kind of think about this in terms of the limiting behavior. As x is getting really big, we can really just forget about everything except the leading terms, right? We can focus on this part. Right? And we could, as long as we're taking a limit at infinity, we can replace this limit with the limit of the ratio of just the orange terms, right? Okay, so what's that going to look like then if we... On the top, we would just get a 2x. On the bottom, we've got an x squared. Now, it's inside a square root, right? But that thinking still applies, doesn't it? Because the x squared term would still dominate. Yeah, we're taking a square root of that, but still the x squared term is going to be the part as x gets really big that the square root is going to be, that's all we really have to consider is the square root of that dominant term. The square roots of the other parts are going to be tiny, right? So on the bottom, we end up with square root of x squared okay. That helps us quite a bit, right? Now that we've got a square root of a single term on the bottom, we're able to do more with that. Square root of a bunch of terms is tough, but a square root of x squared is equal to what? No. Okay, that's its absolute value of x. That's the definition. So The definition of absolute value, the square root of x squared is equal to the absolute value of x. Think about the behavior of that. What does an absolute value function do? If I input a negative number, it makes it positive. If I input a positive number, it doesn't touch it, right? Well, let's call this f of x for a second, or we'll call it h of x, something different. We'll probably save f of x. So if I plug in h of 3, I get the square root of 9, which is 3, right? If I plug in h of negative 3, I get the square root of negative 3 squared, which is also 9, which is 3. Yeah, sure enough. That makes sense, right? This is our definition of what the absolute value function really is. So we replace what's on the bottom then with an absolute value. Okay, absolute value functions are tricky though, right? Absolute value functions, they're not well-behaved functions where they're smooth and continuous. We haven't really talked about continuity yet, but we'll come back and that's our next topic after we deal with this stuff. And we'll come back and kind of take a quick revisit this quickly with the concept of continuity under our belts, and it doesn't really improve anything. It just makes it more succinct, and it makes it probably easier to see. But what do we do with an absolute value function? You can't just do, I can't cross these out because x divided by the square root of x is not necessarily equal to 1, right? I can't remember if I've said anything about, I think I've mentioned it, but there was no reason for you to really remember it. But does anybody remember what our strategy is when we deal with an absolute value function? Okay, I'm going to rewrite it as a piecewise function. Exactly. The definition of absolute value of x is the square root of x squared, right? But if we want to actually do some analysis with that, do something with the function, well, we're going to write it as a piecewise function. Okay? And that guides the behavior. So that is equal to, there's 3 parts to this. It equals x whenever x is positive. It equals negative x whenever x is negative, and it equals 0 when x is 0, right? That'll make sense. I've showed that to you once before, right? Okay. And I know even in Algebra 2, I gave you a hint of that, I remember, but that's been years ago, so you probably remember that. But I think we hit that once this year. Okay, that helps us because now if I know what the absolute value of x is as a piecewise function, I can write this whole function that we're dealing with as a piecewise function, right? Where I'm plugging in the appropriate behavior for the square or for the absolute value of x depending on where we are, right? When x is greater than or equal or is greater than 0, the absolute value of x on the bottom is just going to be an x, right? But when x is less than 0, the absolute value of x on the bottom is replaced with a negative x. Okay, so we could write this as that's going to be cumbersome notation. Let's do this. This will be easier to think about. So everything in the purple circle there, we're going to call that f of x. We're going to define that as f of x. Okay, does that make sense? Okay, is our function defined at 0? Is this purple function, is that defined at 0? It's not, right? Is our original function defined at 0? Yeah, it is, actually. The original function is. So is that a problem for us? Is it? Okay, it's not a problem for us, is it? Because we don't really care. This function that we've used in our limit is fundamentally different from this one. They are not going to look similar at all. They're going to look very, very different, right? But all we care about is the limit when x is approaching plus or minus infinity, right? In that circumstance, they're going to match. In the middle, we don't care. They don't at all, right? But at the tails, they will. So we don't even though the function is undefined here, we don't care. All we care about is what's happening when x is really big positive number or really big negative number. And those are the two behaviors that we get. Everybody see that? Okay. So we could simplify this then. Everything in the purple in here, then we could just break it down. X over x cancels. So I'm getting it equals 2 when x is greater than 0, and it equals negative 2 when x is less than 0, right? Anybody see that? Okay. How come it's 2? Well, because I've got that 2 there. Otherwise, it would have been 1. Okay. And in fact, this is a function that now that you've been introduced to it, you probably kind of want to remember this one. Let's just put this, I'm going to put a little spot down here at the bottom. The absolute value of x over x is the same as its reciprocal, and it is equal to 1 when x is positive and negative 1 when x is negative. It's just a step function, and that's the behavior of that function all the time. That's what it always looks like. And it's undefined at 0. Yep. Mm-hmm. X cannot equal 0. Okay, and we'll look at a graph of that in a second. Okay. But if that's our function then, well, the limit's pretty easy to take, isn't it? Right? What's the limit? The limit of f of x as x approaches positive infinity is what? 2. Everybody agree? It's 2. As x approaches infinity, the value of the function is exactly 2. Okay. The limit of the function as x approaches negative infinity is negative 2. Yep. Okay, let's look at a picture of this thing. How about? Where is that? Right there. Yeah, there's our, okay, there's the original function right there, isn't it? Okay. And if I graph the asymptotes at 2 and negative 2, sure enough, it sticks to those, right? Now, what's the function we use to take the limit? We use the blue one. Is the blue one anything like ours? Where is the blue one? No, I shouldn't have to. Oh, maybe, is it? Oh, there it is. I got to really zoom in. I think. Oh, what am I saying? I know what it is. It's going to exactly match up. Yeah, duh. There's the blue function, right? Okay. Why is there that little jig right there? It shouldn't be there. It's not actually there. That's just a graphing error. Because Desmos is a numerical tool, it's going to make some mistakes in graphing sometimes, and that's a mistake. What should really be there at the endpoints? Open circles, right? Okay, I wonder if it does better. Let's just see what happens if I do. How about if I graph y equals, here, let's do this. I'm going to do x divided by absolute value of x. And okay, it does better with that. For some reason, it's the square root of x squared part that messes it up. Let's make this different color. How about if we make this like orange? Okay. And then all I'd have to do to that function is multiply it by 2, right? And look, it does a good job. The orange function and the blue function are identical, right? Because the definition of the square root of x squared is the absolute value of x. But for some reason, there's that little glitch when you graph it with the square root of x squared. I don't know why. But that's what our function should look like right there. Okay. And if we want to, yeah. How could I put, just to make this graph look better, just challenge your thinking here for a second. How could I get this thing to have open endpoints at the endpoints? I have to I can't really do it. I have to just sort of trick it. It's almost like just, I'm going to purposely draw endpoints there to make it look right. I could write a piecewise function, but I could also just graph 2 points, right? I could graph in Desmos, and you guys want to get, I tell you what, you want to get good at using Desmos and all these graphing tools, because in college, more and more, this is what you're doing. Like I just talked to Andy yesterday, and he, how much stuff does he do on paper in his calculus class? Even though it's proof-based calculus class, nothing. It's all, everything is done. It's kind of cool. You walk in with an iPad, and they've got this program where you walk into the room and automatically it just populates the iPad with all the stuff that that you're looking at, and then you can graph on it, and it sends it to your online notes, and it's really cool. But it's all done like they're using this stuff all the time. Just so this is what you're likely to see in college more and more. So we could just graph an ordered pair. I could do the ordered pair, 0, 2, 0, 2. And then I'll put along with that, comma, another ordered pair, 0, -2. And I could make those, if I really was going to be particular about it, I would just do something like that, right? Make them orange, and I'd click the open endpoint, and that's what it should look like. Okay, yes, sir.
So you don't use like a different graphing website.
Other than Desmos? Like which one?
I don't know. Exactly. That's why.
Well, because a couple of reasons. Because Desmos is free, it's open source, it gets improved every year, and now that's a big thing. I mean, you could use something like in college, we used Mathematica, which is really expensive, and Maple would be another one that's a really big one. I mean, you can do all kinds of crazy stuff with it, but it's extremely complicated to use. It requires, and it's at some point that's probably what has limitations, but for most of what we do, man, this works pretty great. And you can do stuff on here. I've showed you guys how to generate tables and things from a function. You can do that. You can even do now, I haven't even played around with all this stuff, but in Desmos, yes.
How much does it cost? The mathematical one.
I don't know what it is now. I think you can get like a student version of Maple for $80 or something, probably. Look at the math tools you got here now, though. You can do matrix calculators. That's pretty cool. You can do a bunch of matrix, linear algebra stuff. I don't know what the test practice is. I have no idea. What is that? Choose assessment. You gotta be kidding me. What are we doing here? What?
State testing?
I guess. Well, who cares about state tests? I was hoping they were going to do something on there about like SAT or.
Khan Academy.
Yeah, Khan Academy is the one to use for SAT stuff. Yeah. Huh. Interesting. Wow, there's all kinds of new stuff here. Oh my goodness. I got to look at this a little more closely. Wow. Okay, I don't need to do this now. I'm eating up calculus time, but wow. This is a good toy. Okay. I'll take a picture. We'll get on with more math. Okay, give me 1 to 5 on that. I got sidetracked, but are you guys feeling okay on what we just did there? Okay. There's our picture. All right. Okay. Why did I do that? I guess it's review. So which power function models the end behavior of this function? Everybody just think about that on your own for a second. Jot it down on scratch paper. What's the power function that's going to model the end behavior? Negative 3x cubed. Everybody get that? Right, because we're just going to look at the ratio of the leading terms. Okay, so this is the stuff. If you look at all that stuff right there, g of x would be negative 3x cubed. And if I do, can I click on this, I hope? No. This is probably overkill, but I just want to show you, I go through this one more thing here. So if we graph both of these, what do we have? Negative the quantity 6x to the fifth plus 7x squared divided by 2x squared minus 11x plus 27. Is that right? Yeah, looks good. Oh, 7x squared, yeah. Okay. So there it is. There's the original function, right? And if I zoom in all the way, I probably get, I get some complicated behavior where it looks like it's got a minimum there and it's got a maximum there, right? So there's some little subtleties that g of x is not going to capture, but g of x is negative 3x cubed. However, if we look, that one, equals negative 3x cubed. Look, they don't look similar if you look close to home, right, for small values of x, but if you zoom way the heck out, they're going to start to look more and more similar, right? The end behavior is going to match up. That's the whole point. And I probably didn't even need to do that, but you get the idea. Okay. Okay, so now what's the order of the polynomial that model, or the power function that models the end behavior? What is going to be the power function that models the end behavior? What's it going to be? 3x. Okay, so it looks linear, doesn't it? Okay. So if it's linear, do you see potentially an advantage to that? So this rational function, the limits at infinity, it's not going to give us a horizontal asymptote, right? But I'm dividing a quadratic function by a linear function, which should give me a linear result, right? Now, it may not be a true linear function, but the polynomial I would get out of that, the polynomial part's going to be linear, right? Do you see some potential benefit to that? I mean, like, asymptotes are really useful, and you guys don't know this yet, but one of the big things we're going to do in the future is we're going to, once we know some calculus, we're going to try to quickly sketch a graph of a function with all the important details included. So the points that are going to be the minima and the maxima, the points that the ordered pairs that correspond to the inflection points. We want to know where the zeros are, where all the asymptotes are. And we don't really care about a graph. We just want to sketch so we know what the values of the function are at these important places, because these functions model, behavior in physics or in the economics or something. And so we want to be able to use these functions and analyze them quickly, right? So asymptotes play a huge role in that. If we can draw the asymptotes up there, it's really simple to get a sketch of the graph because we know they stick to the asymptotes, and so it limits the possible different shapes that the graph could have. So even though there's not a horizontal asymptote here, is there potential for something else valuable? Say it again. Well, maybe a hole, okay, but also if I divide a quadratic polynomial by a linear polynomial, I'm going to get the polynomial part of that quotient is going to be linear, right? So even though it's not horizontal or vertical, it's got some slope, presumably, it still could act like an asymptote. It could act like a slant asymptote or an oblique asymptote. Do you remember I actually forced you guys to do this a couple of years ago? Do you remember calculating oblique asymptotes in Algebra 2 at all? Not so much? Okay. Okay, it's been, but it'll come back to you because you did it once, so it'll come back to you. So in that event, if the numerator, the order of the numerator in a rational function is exactly one greater than the order of the denominator, you can divide this out and come up with the equation of the slant asymptote pretty easily, right? So think back to pre-calculus. What's the easiest way to divide out, to simplify that quotient? You got two choices, right? Long division, polynomial long division, or synthetic division. Which one would we want to use here? As you guys, is this not remembering this stuff?
I forgot to do it.
Well, okay, that's why, good thing we're going to review it then, huh? So this would be synthetic division. Okay, we'll look at some examples where we have to do long division too, but synthetic division is the one we can use if we have a linear factor in the denominator. And it's much, much easier to do if the linear factor is, if the coefficient of x is 1. Okay, so if it's x plus or minus some number, yes. Say it again. If what's a factor? X minus 2? Because there's only one factor in the denominator, right? There's only one thing. If I group that, it's not x minus 2 times, it's not like x times the quantity x minus 2. That would be two factors. It's just an x minus 2. Right. We got one factor on the bottom and we've got one factor on the top, a monomial on the top. X squared technically you might think of as two factors, but we can just think of it as one factor also, right? So if we're going to divide this out using synthetic division, see if this rings a bell, right? So we're going to make our synthetic bracket. And what goes in the top row of our two rows in our synthetic bracket? You remember that? You have to put the coefficients of the numerator, right? For all the, this only works for polynomials, dividing polynomials, right? So we have to have each term, we can't skip any, we have to have the coefficients of all the terms in that polynomial. Well, how many terms in general are in a quadratic polynomial? You got the x squared term, the x term, and the constant, right? So there are three terms. I need coefficients for all three terms. Well, what's the coefficient of the quadratic term? 3. What's the coefficient of the linear term? 0, because it doesn't show up. What's the constant? 0. Just ringing a bell now? Okay. And then remember, we put below the constant, we put our remainder box. Okay. And how did we do it? What goes out front? Yeah, the 0 of the denominator, right? Which would be 2, right? And then we just do our synthetic process. Then we just pop the 3 down below the bracket. And as soon as a number appears below the bracket, we always have the same little algorithm. We're going to multiply that number times the front 0 and add it. We don't, subtracting is what we do with long division. We do the opposite. We add with synthetic division. So 3 times 2 is 6, plus 0 is 6. 6 times 2 is 12, plus 0 is 12. So we have a remainder of 12. So what's that telling us then? What's this equal to? What's this part telling us? It's going to be 3x plus 6, right? This gives us the coefficients of the polynomial portion of our answer, right? So we always, and the way to do this is you always, You want to start with the constant and work your way backwards, or it's easy if you have a lot of numbers there. It's easy to lose track of what goes with what. Well, I know the remainder box is always next to the constant, so that's a 6 plus a 3 times next up would be an x, right? X to the 1. So I get 3x plus 6 plus, what's that telling me? The 12. Yeah, that's the remainder, right? And what's the remainder do? The remainder is what remains over the denominator. Okay. So we get a 12 divided by x minus 2. So there's my answer. Okay. That is what that quotient is exactly equal to. We simplified the quotient, right? So that's another way to express f of x. Instead of as a rational function, we're writing it as a polynomial plus a remainder, right? So then we're interested in the end behavior, right? So the limit don't do that. Limit of f of x as x approaches plus or minus infinity is the limit of all that stuff, right? Okay, in the limit that x approaches plus or minus infinity, do any of those terms go to 0? That one does, right? The remainder term always is going to go to 0 because the remainder term is always going to have you're always going to have a bigger degree polynomial in the denominator than the numerator, right? You're going to get a number on top and a linear polynomial on the bottom, right? And so this one goes to 0. So that's gone. And yeah, sure, that first term is going to dominate, but when that goes to 0, this tells us exactly what the equation of that slant asymptote is going to be, right? It's going to be the line 3x plus 6. Because as x approaches infinity, this other term just goes away, right? It becomes insignificant. Now, if x is very close to 2, this term is going to dominate, right? Because the denominator is going to get big and that term is going to dominate. But as x approaches infinity, once we get far away from 2, this is the part that's going to be important. So we end up then with the slant asymptote. Sometimes we call it an oblique. Is just the line y equals 3x plus 6. Let's look at it. I'll show you. So 3x squared over x minus 2. Okay, so there's that function. Kind of weird, right? Let's look at the equation of our asymptote. Y equals 3x plus 6. Okay, and if I zoom out, see what it does? Okay. It does stick to that. As x gets big or small, you can see the function sticks to that line. and it guides the behavior of the function. That's pretty cool. Yeah.
Does the can the blue line is the straight line on the asymptote?
Can it? Yes, it could. It could cross it. Yeah. Yeah, it could cross it. Mm-hmm. So are there any other asymptotes in that blue function that we maybe should draw? Yes. How can it cross the slant asymptote? In the same way that I think I have something up here. Oh, did I right over the top of that? Yeah, I did. But how about this? What if I do f of x equals sine x squared over x? Sine x squared. Or I could even just do sine x over x. I don't even have to do sine x squared. Sine x over x. Right? So isn't the asymptote there y equals 0? Right? It's going to cross that asymptote an infinite number of times, but it's always going to get closer and closer to it as you move further away to the left and the right. Okay, and a slant asymptote would act the same way. Now, a vertical asymptote, you can't cross. You're exactly right about that. Yep. Mm-hmm. It doesn't cross in that one. Mm-mm. It doesn't cross. I can't remember where that one even was. It's right there. Okay. Are there any other asymptotes though? Look at the f of x. Are there any other asymptotes we could identify? At 2, we're going to get a vertical asymptote. How come? Bottom 0, but the top is not, right? 2 is a unique 0 of the denominator. Okay, not the numerator. So we could also graph, if we really wanted to get the skeleton of this function, we would just graph the asymptotes. So x equals 2 and color. And then notice how that really gives us, just those asymptotes give us a pretty accurate idea what this function is going to do. What are the options? There really aren't much in the way of options. Either it's going to be doing this or it's going to be doing something like that. It really narrows it down, right? So having those asymptotes is very, very useful. Okay. Okay, let's look at another one. So, and again, how did we identify right away that this one was worth dividing out? Whereas if I had looked back at something like that guy, there's no reason for us to do that long division, right? That one would be a waste of time. This one, it paid off to divide those out. How come? Am I going to get a slant asymptote there? You're right. How come? What's the difference? Well, it is, but that's not why. Yeah, okay, good. Because the power, the order, or the degree of the numerator is not 1 greater than the denominator. It's 3 greater. So I'm not going to get a line out of that. I'm going to get a cubic polynomial if I divide that out, right? Which isn't much use to me. Only a line is really useful because it's so easy it's an asymptote. Okay. All right. How about that one? Is that worth dividing out? It is, isn't it? Right? Okay. Try it real quick. Find all the asymptotes for that function. You do the opposite of long division, so you add. Oh my goodness. We don't really care. Honestly, all we need are the first, right? So we know we're going to get. Okay, we don't really care what that big number is on the top, right? Because when we take the limit, that term's going to go away.
Use the main entrance as the road on 14th is closed for road construction. Again, students who will be leaving out of the parking lot for lunch, please use the main entrance as 14th is closed for road construction.
Okay.
Thank you.
Everybody get that? Because in the limit, if we take a limit as x approaches infinity, this term right here is going to be the one in our limit. That one's going to go to 0 because I have a constant, even though it's a big number on the top, it's a constant divided by x plus 18. So as x gets infinitely big, that's going to get driven to 0. Okay, and so that's our slant asymptote. What's our vertical asymptote? Vertical asymptote, x equals negative 18. Okay, and we know that because negative 18 is a 0 of the denominator, but not the numerator, right? Okay. Give me 1 to 5. Does that make sense?
What would you do if it was also a 0?
Okay, so you tell me, what would you do if 18 were also a 0 of the numerator, then what do we have to do? I mean, in other words, that means the limit of this function as x approached negative 18 was 0 over 0. So it's indeterminate, right? It could either be a whole or a vertical asymptote. We have to actually figure out which. We have to resolve the indeterminacy until we either get an answer, a finite answer, which means it was a whole, or we get an infinite answer, which means it's a vertical asymptote. We get a number over 0, right? Okay, that's that stuff we talked about. Was that yesterday or the day before? I can't remember. It might have been the day before yesterday, I think.
I forgot how you
Yeah.
solve that. Multiply it by x minus 18 or something over x minus 18.
What's that?
Like, how would you go about solving?
Go about solving. Well, you'd have to factor the top and you'd have to cancel an x plus 18.
Oh, you have to factor it.
Mm-hmm.
But what if it doesn't factor?
Well, then you wouldn't get 0 over 0.
Oh, yeah.
Yeah. Yep. Oh, question?